Now I'm ready. Thank you very much, Konstantin, for the introduction. So in this first talk of today's webinar, I'd like to give a very simple overview on what the software package FHI-aims is and why it may be the best option for your needs. The title of my talk is also the title of a recent publication that we have been preparing since the beginning of this year. And since October 1st, it is largely ready. This publication has been a big project, and essentially all colleagues from around the globe who have contributed to the developments or advancements of FHI-aims software are authors. They have contributed to at least one of the 32 topical contributions. The current version of the manuscript is available on request. Just send an email to our secretary, Anna Lutz. Obviously, it is not possible to cover all 32 contributions in a 30-minute talk. Thus, I will only have a little glimpse at this roadmap and will discuss very few selected examples. Here you see the FHI-aims webpage. FHI-aims is an all-electron code which employs numeric atom-centered orbitals as basis set. I will explain this concept in a moment. The key characteristics of FHI-aims are summarized under these yellow buttons here. It's versatile, precise and accurate, and scalable. Versatile means that FHI-aims can handle molecules and clusters as well as nanostructures, surfaces, solids, and liquids. It has the option for treating finite systems as well as extended materials. It is precise and accurate. And this means that FHI-aims treats density functional theory with the best advanced functionals, also including van der Waals interactions needed for describing, for example, organic systems. It also offers many-body methods, which means GW and BSE, and includes coupled cluster theory. And FHI-aims is scalable, which means that the code runs on laptops for small and reasonably sized systems. For bigger systems or for long-time molecular dynamics, FHI-aims runs extremely efficiently on high-performance computers. The software is owned by the non-profit association MS1P, and this association was established under German law, and therefore it reads eingetragen, gemeinnütziger Verein, gemeinnütziger eingetragener Verein, which may be translated as non-profit and charity association. The association is led by an executive board, and here you see me, the chair, Volker Blum and Mariana Rossi. The work or the workload of these three people is significant, but it is 100% voluntary. So these three people do not get a penny for their work. All income that MS1P receives goes back into maintenance and developments of the software of the FHI-aims project. Currently, the association has 5 employees. They are also here at the webinar. We have Anna Lutz as the secretary. Sebastian Kokott is leading all MS1P activities together with the executive board. Sebastian, Konstantin, Andre, and James are involved in various organizational, maintenance, bug fixing, coding activities, and outreach. Now, the central decision behind FHI-aims, which was taken in 2003, was to employ numeric atom-centered basis set. This concept was very much the result from numerous discussions I had with Bernard Dely, and therefore in my group, Jörg Behler was using Dely's DMOL code for surface calculation for his PhD since 2001, also doing some software developments. The motivation behind the development of FHI-aims was to reach highest accuracy, highest precision, and highest numerical efficiency. We also concluded already back then that the future of computing will be massive parallel, and we saw the needs for using exchange correlation functionals that include exact exchange. Since 2005, Volker Blum became, and now is, the undisputed leader of the FHI-aims software developments, initially in Berlin and since 2013 at Duke University. So this is how our basis functions look. They have the relevant oscillations close to the nucleus, and for larger distances, they decay to 0, which is enforced by adding a repulsive cut-off potential to the Kohn-Sham effective potential of the free atom at larger distance. This potential is noted here in black. You know that in pseudopotential theory, these oscillations are smoothed away. So this basis set has the advantage that it is chemically meaningful. It is naturally all electron. It is strictly localizable, which implies an order n computational scaling for most expensive numerical steps. And this basis set is very compact, and still it is accurate. We have a basis set library for all elements from Z = 1, hydrogen, to 102, which is nobelium. And there are choices for fast calculations and more qualitative results, two calculations which are very highly precise and have many milli-eV precision of the computed DFT total energies. In simple words, this implementation is more precise than plane wave pseudopotential calculations, and despite it is all electron, it is numerically not more expensive. It may be even faster. More details about the basis set, also for correlated methods and the treatment of relativity and spin-orbit coupling, are described in chapter 2 of this roadmap. This is actually the only chapter where some contributions are still missing. 2.1 to 2.4 are still on Volker Bloom's desk, but I understand that they will come very soon. One aspect of this chapter concerns the support and usage of common and supported libraries, including the noted ones here, the ones which are noted here at the bottom. Some words about 2.6 electronic structure analysis tools. Let me here just mention that this contribution describes how band structures or wave functions or orbitals or SDM images and much more can be plotted and can be analyzed. The discussion of 2.5, namely the eigenvalue solver, ELPA, I like to combine now with chapter 3, which deals with exchange and correlation. In fact, the main computational bottleneck for accurate and precise electronic structure calculations concern these two issues, namely the evaluation of known local exchange and the evaluation or the performance of the generalized eigenvalue problem. Let me mention one example here that demonstrates the recent advancements in handling these two aspects. This is probably a world-leading example that is a calculation that was not possible 2 years ago, hybrid DFT studies for very large systems. This figure summarizes the computer time for systems of different sizes. That goes along the x-axis, 3,000 atoms to 30,000 atoms. The y-axis displays the wall clock time. The known local exchange correlation part is shown in blue and the eigenvalue problem in red. At the very left, you see the layered perovskite, which is a phenylethyl ammonium lead iodide, an important battery material with a defect complex. Here, the hybrid functional needs most of the time, but when we go to bigger systems, more to the right, the eigenvalue problem treated by ELPA is getting increasingly more costly. At the very far right, you see what is possible today. This is water in the IS-11 structure with 30,500 atoms and using the HSE exchange correlation functional. All electron methods, which I know, stop at a size well below 1,000 atoms, often at around 100 atoms. And this figure for AIMS here starts at 3,000. For chemical reactions and chemical reactions in a realistic human or wet environment, or for electrocatalysis, such big systems are important indeed. Because of the massive parallel implementation, the time is still very reasonable. And let me add that a more recent development of ELPA using GPUs, in this more recent development, the computer time is reduced even more to about 2/3 of the value that you see here. The future of DFT calculations will be more and more with hybrid functionals, PBE0, HSE, and alike. Here, I show a figure that displays what features are currently implemented in FHI-aims and which functionals are accessible or are offered. So these are the functionals which you can use in FHI-aims in this green part. And in this bluish and yellow area, we have various analysis tools and quantities. Obviously, we have band structures, but we can also get information about, say, crystal orbital overlap population and much more. Here down, we list the van der Waals corrections, because also hybrids are missing the long-range correlation effects. A special contribution of the roadmap deals with this topic, namely with numerous dispersion post-SCF and full SCF van der Waals dispersion methods. The contribution in the roadmap discussed the Tkatchenko-Scheffler TS model, two variants of the many-body dispersion, the exchange hole dipole moment, XMD method of Aaron Johnson, and we also have the DFT-D3 approach of Grimmer. Both TS and MBD are also implemented with full self-consistency, meaning that the van der Waals dispersion interaction not only affect the energy and forces or stresses, but they also affect the electron density, the orbitals, and all the properties derived from the orbitals and electron density. These aspects can be important for large and for polarizable systems. So this is chapter 3. Actually, in addition, what I've discussed, 3.1 to 3.3, we have 3.4, namely the random phase approximation, which we have in AIMS since several years, and now also with forces. Let me remind that the random phase approximation is classified as a highest rung of exchange functionals just below heaven. Over the past 2 decades, it has gained recognition for its ability to accurately capture known local electron correlation and known local electron correlations and effectively describing, it can describe subtle energy differences. This brings me to chapter 4, electronic excited states. This chapter discusses coupled cluster theory. It discusses the GW method, time-dependent density function theory, and delta SCF. These implementations cover neutral excitations as well as ionization and electron affinities, which means charged excitations. And we can do this for core levels and for valence bands. And we can do this for finite systems as well as for extended solids and liquids. Very briefly, about the W implementation here for finite systems, they come in different flavors, as indicated by this figure here. Obviously, there is the G0, W0 approach, but several other improved developments are available as well. There are different frequency integrations and vertex corrections, and so on. Let me mention some words about the coupled cluster implementation. This is done by a linkage to the CC4S code by Andreas Grünheis. We have coupled cluster theory for the ground state, and now we also have it for excitations. As you know, for the ground state of molecules, coupled cluster theory is considered the gold standard in quantum chemistry. These quantum chemical methods have a somewhat complex dependence on the basis set. That is, one needs to use so-called correlation consistent basis sets, and one then needs an extrapolation to what is called the complete basis set limits, where you see actually here 2 extrapolations. And you see our results compared to a leading quantum chemistry result, which obviously works very well. And on the right side, you see what is now the standard in doing excitation state, excited states, with the so-called equation of motion. Our results are in pink, and the leading results from quantum chemistry are in green. I think also very good agreement. Now, for extended systems, we are currently facing some numerical challenge, because the K summation is currently not performed explicitly, but it's done via increasing supercell sizes. This is inefficient, but worldwide competitors are facing the same issue. Here you see the example on the finite size supercell convergence of the cohesive energy of neon. This is plotted against the RPA result on the left. And the extrapolation of these 4 calculated points to the K converged level is here. And we get two numbers, one actually for the coupled cluster single-double and the other for the coupled cluster single-double perturbative triple. I think in good agreement with experiment, the experimental value I think is 27 millieV per atom. On the right side, I show the electronic band gap of two-dimensional boron nitride for 4 different supercells, 2x2, 3x3, 4x4, and 5x5. And the extrapolation, and you see this in comparison with HSE and some other many body methods. The green area here shows the uncertainty of a diffusion Monte Carlo result. Let me say that such excited states for extended systems require big supercells and therefore are not really practical. They need too much computer time. Thus, better methods are needed. For the ground state, the left picture, things are working well under control, but for the right, I think we still need improvements. But as you can see, if it's converged, then it really works. And here's again the contents. Oops, where is it? There. The contents of the excited states chapter. We already discussed GW and coupled cluster theory, but let me say some words now about the time-dependent density function theory. Contribution 4.5 in particular, let me go to this, describes the explicit real-time propagation approach for time-dependent density function theory. This approach allows to expand the applicability of FHI-aims beyond the linear response or the traditional perturbative regimes, which will be discussed in the next chapter. Such real-time dependent density function, this real-time time-dependent density function theory simulations can address important questions, especially pertaining to known equilibrium, electron dynamic phenomena, including interfacial charge transfer, atom cluster collisions, topological quantum matter, and more. Furthermore, with this theory, Ehrenfest dynamics can be performed on top of real-time dependent DFT so that known adiabatic effects of electrons can be taken into account in first principles molecular dynamics simulations. This is discussed in this section. And finally, in section 4.6, the authors discuss what is called constrained density function theory. This means that one calculates total energy differences of the ground state and of constrained, that means excited states. Specifically, this contribution discusses the occupation numbers, situations where the occupation numbers are reduced, for example, the occupation number of occupied states are reduced by 1, so creating a hole, or occupation numbers of unoccupied states are set to 1, that means creating an electron. In this way, X-ray photoelectron spectroscopy and X-ray absorption spectroscopy can be simulated. This brings me to chapter 5, which is entitled Linear Response Theories or methods. It starts with density functional perturbation theory, which extends the framework of DFT to the calculation of response properties of the electronic density. DFPT can give access to a large variety of properties depending on different external stimuli that generate the perturbation. An incomplete list may include force constant matrices, phonons, molar polarizabilities, dielectric properties of solids, electron-phonon coupling, known adiabatic matrix elements, also nuclear magnetic resonance, shifts, and more. All this is described in the first 2 contributions of this chapter. And contribution 5.3, called polarization, Born effective charges, and topological invariance, largely deals with the Berry connection, with the Berry curvature, and the Berry phase. These are key properties describing the reciprocal space topology. They provide a profound link between the phase of a quantum wave function and macroscopic observables, as well as materials properties. Most prominently, these quantities are central to our understanding of topological materials, and they provide a route to classify phases in terms of topology. For instance, all the aforementioned quantities enter the definition of the topological invariant, which is called Z2. Chapter 6 deals with essentially all aspects of vibrations and ab initio molecular dynamics. This includes essentially all aspects of phonons, but it also covers strongly anharmonic materials where the phonon lifetime is comparable or even shorter than a single oscillation. Then, obviously, the phonon picture is getting invalid. This is also called or described in terms of the Joffe-Regel limit. And here you see an example where the limit is violated. 6.2 concerns ab initio molecular dynamics. As you know, ab initio molecular dynamics connects the fields of electronic structure theory and statistical mechanics. It shows, or it allows us to compute and to analyze and to understand thermodynamic processes and properties, as well as the kinetics. This contribution also describes interfaces to other codes and workflow engines, for example, or in particular, IPI, ASE, and FHI-aims. As an example of the grand, they show and discuss the grand canonical replica exchange molecular dynamics approach. Now, FHI-aims also offers the treatment of materials where the quantum nature of the nuclei is important. And they discuss in 6.4 electron-phonon coupling and electronic friction. Particular for metals, phonons effectively couple to low-energy electron-hole pair excitation. In this situation, standard molecular dynamics techniques neglect the energy transfer between lattice vibrations and electronic excitations and can provide qualitatively incorrect dynamical properties. This contribution in the roadmap, for example, discusses how such energy transfer can be accounted for through what is called molecular dynamics with electronic friction. An important concept for the numerical description of anharmonicities. Oops, I wanted to go on. To describe anharmonicities and to study excitations and transition, phonon-induced transitions or lifetimes, is the band structure unfolding from large supercells back to primitive cells. This is discussed here for the cone-sham band structure and also for the and in this paper, it's also in fact discussed for the GW self-energy, where you then have the finite lifetime effects due to the electron-electron and the electron-phonon coupling. 6.6 then is entitled Computing Adiabatic Couplings. Let me just explain what this means. We know what we mean by adiabatic states in the DFT picture. These are well-defined delocalized cone-sham eigenstates. However, localized diabatic states are not unique and must be approximated. A large number of diabatization methods have been emerged to determine suitable diabatic states and the coupling between them. For FHI-aims, two efficient approaches are currently available: the so-called fragment orbital DFT and the projection operator diabatization. These methods are, for example, needed to describe charge transfer in molecular systems. At surfaces, they enter theories of chemisorption, and they are relevant in catalysis, in scanning probe microscopy, and more. Chapter 7 deals with various aspects and various forms of transport. With respect to the description of vibrational heat transport and electrical heat transport, FHI-aims features the most accurate methods considering the full statistical mechanics and all degrees of anharmonicities. In other words, the underlying theories are those of Green-Kubo and of Kubo-Greenwood, and the next talk by Christian Carbonio will describe the methods and what you can do with them in more detail. Contribution 7.3 deals with molecular transport. This contribution addresses single molecular junctions and nanoscale systems where a molecule is connected to metallic electrodes. These systems have revealed a wide range of remarkable quantum phenomena, including quantum interference, non-equilibrium spin crossover, and much more. The focus in this section or in this contribution is on the ab initio transport simulation package, also called A-trans. Chapter 8 then is the final one. workflows, and artificial intelligence. Let us have a brief look at these 4 contributions. With routine access to petascale computers and increasingly to exascale computing, our field needs more efficient tools and infrastructure for creating or managing large data sets, visualization and analyzing diverse data, and assessing the quality of simulation results. FHI-aims offers numerous tools for these purposes. Let me just mention GIMS, our graphical user interface. This is a browser-based toolbox which also facilitates the generation of input files for basic workflows along with the analysis and visualization. FHI-aims is employing further more numerous developments of other groups. In particular, it integrates with the, this is here, with the ASE, Atomic Simulation Environment of Christian Thyssen's group in Lyngby, and the Python Materials Genomics Library from the Materials Project of Christine Persson and Gerd Zeder in Berkeley. These 2 widely adopted frameworks enable to concatenate many calculation steps and automate their execution. And there is much more, as you can see here, but I don't have really the time to discuss this here. It's all discussed in the roadmap. Contribution 8.2 discusses explicit and implicit embedding approaches. We had seen previously that FHI-aims can treat 10,000 water molecules even at the hybrid level. However, for some questions, we may need even more molecules, or we like to save computer time. In order to maintain a high level of precision, contribution 8.2 discusses hierarchical representations where the all-electron region of interest is embedded within a coarser representation of the environment. The most common fields of application for such multi-scale embedding is biochemistry, but there are also other fields, as for example, homo and heterogeneous catalysis, crack propagation in materials, and more. 8.3 is called Workflows for Artificial Intelligence. Now, everyone is talking nowadays about AI and machine learning. However, often these tools are used somewhat careless. This contribution in the roadmap addresses workflows that automate the intelligent, that means AI-guided acquisition of data, and it describes the AI-guided exploration of material space. We discuss the creation of machine learning interatomic potentials, also stressing that they may provide an unreliable description because they're overlooking, for example, rare events. It is shown how this can be prevented by looking at uncertainties and to improve MLIPs with data points where these data points are needed. This is also the next example, as in the next example, an active learning strategy. Many materials problems are high dimensional in nature and involve costly evaluation of an objective function. Here, active learning can dramatically reduce sampling, and one contribution in the roadmap describes the Bayesian optimization structure search method, also called BOSS. This algorithm builds probabilistic n-dimensional surrogate models for materials energy, starting from FHI-aims for the energy and for property landscapes, and then refines them with smart sampling. In a similar spirit, but using a very different AI method, the example on the right side describes the integration of FHI-aims with the AI method called CISO. Here, one may create a map of materials properties and functions to identify the region of interest of interesting materials. So before really doing calculation, one can see that the interesting materials should be actually in this region, and one should concentrate it here. In this region of material space, we already have enough data, but you need the right descriptors, that means the right X and Y axis. Machine learning, the electronic structure in a real space and atom-centered framework. This is contribution 8.4. This contribution describes machine learning methods that target the electronic density or the Kohn-Sham Hamiltonian. This here is a sketch of the ecosystem of machine learning ML methods for the electronic structure that are interfaced to FHI-aims. Specifically, these are salted, a symmetry-adapted Gaussian process regression approach. There is row-learn, there is DOS-learn, and on the right side, you see deep H and ACE Hamiltonians. This brings me to the conclusion. I hope that I could give you a little bit of an idea of the many aspects that can be addressed by FHI-aims. Obviously, my presentation was shallow because the roadmap of advancements of the FHI-aims software package is truly extensive. It is impossible to give a complete overview over what is covered in the or described in the roadmap. And when I agreed to give this talk today, I agreed on that 3 months ago. I was clearly naive that I would be able to really give a good description. I'm sorry for the incompleteness. One important point I like to add is that most contributions of this roadmap also contain web-based tutorials that help newcomers to use and better understand the methods. Let me thank the many authors of this roadmap. I discussed their contributions, but this was clearly incomplete. I already apologized for that. But in particular, I like to apologize that it was not possible to cite the people properly. There are simply too many. Thanks also go to the FHI community. FHI-aims is, and you may have seen that, a product of a very large community, developers, but also even more users, without whom this code would not exist the way it does exist. I thank clearly the MS1P team for their great work, and I thank you, the audience, for your attention, and I'm now happy to receive questions. Thank you.
Thank you, Matthias. I think it was a very nice talk. Yeah, there's already a lot of clapping emojis from the chat, so the people clearly enjoyed it also. So now it would be time for the Q&A session. And here we'll hand over to my colleague, James Green, who will take over the moderation for the Q&A. So thank you again, Matthias, and then see you in a bit.
Yeah, thanks, Konstantin. Yeah, thank you, Matthias, for the talk. So yeah, if anybody has questions, then the people in Zoom, you can enter them in the Q&A session. Or if you prefer to speak your question, you can raise your hand and I can unmute you. And for colleagues watching on YouTube, you can enter it in the chat, and also Kusha, you can enter in the chat as well there, and we're monitoring both. So already a question from Robert Moll. Can one compute IR intensities for extended systems?
I have to say that we have not done that. So I believe one can, but I'm not completely sure. For Volker, do you know that? Have you done something similar on that line?
Can you repeat the entire question? Sorry.
Yeah.
I was trying to understand, but yeah.
So it's written in the Q&A. If you look in the so the question, if you can infrared spectra.
Oh, here's the Q&A. Sorry, that's what I'm trying to look at.
Yeah. So can we calculate the full spectra? Is the question.
Raman, Christian, I think. Raman certainly.
So we have done Raman, but we could also do IR. I think we've never done it explicitly, but everything is there.
Yeah.
And just to follow up, emphasis on the intensities, not just the frequencies.
Yes, I mean, you have to basically look at the responses and then you can do IR in principle as well. We've never done it, and I don't think there is a script in place to really do it automatically. But if one is interested in that, just contact me. I think everything is there in our FHI-aims Python package to then extend it to also calculate IR if necessary.
Yeah, exactly. That's what I'm also just I think from this. I don't know if there's a script, but that should be doable.
I think it is doable, but I think there's still, in general, I think questions really about how good the intensities are at the end, right? I think that the energies are fine, but the intensities are sometimes not captured as well.
Yes, Matthias, you're right. I mean, that depends very much on the level and the accuracy of the electronic structure theory and the response method used. I mean, there's also open room for development to make these methods better.
Okay, thank you all for the answers. So we have another question, anonymous attendee. For Bayesian optimization, how the priors and electronic structure theory problems are chosen?
Okay, I have to say, actually, I have only read the paper, so I've not. I mean, this is the BOSS method by Milica and so the Finnish people. No, I cannot really give I don't dare to give a knowledgeable answer. I could only repeat what I've read. I'm sorry.
But yeah, if you're interested in this, then yeah, reading this chapter in the roadmap and the authors of this chapter can definitely help you out with that.
Yeah.
Okay. So another question from Shubham Singh. How expensive lattice thermal conductivity calculations are compared to other codes, I think?
Okay. I mean, so what we are doing is really the full methodology which is necessary for anharmonic systems. If you have a largely harmonic systems, then actually Boltzmann transport is the matter of choice, and it's much faster. But of course, if you don't know if it's really medium or actually strongly anharmonic, I think there is no other choice than doing what we are doing, and I don't see that any other implementation would be faster than what we have. Now, this implementation was done by Christian Carboni, who is giving the next talk, and you can probably add a little bit to that. But I think if you want a reliable answer, there's nothing faster than what we have. If you are sure that this is harmonic, then you should actually do the Boltzmann transport.
Yep. But I mean, just to chime into that, I completely agreed with what Matthias says. We have both Boltzmann and a more actually fully unharmonic green Kubo in FHI-aims. And I would say for the Boltzmann kind of calculation, I would say we are comparable, if not faster than most other electronic structure codes. And for the green Kubo, I would dare to say that we're an order of magnitude faster than competing implementations.
Question with this, and just add to this point, so if you're interested in seeing how fast this is, then we have the tutorial session tomorrow. So if you're registered, hopefully you've already got the access credentials for tomorrow, and if you haven't registered, then you can still do so. Just contact us and we can give you some credentials to try it out. Okay. So a question from Sushant. Can we do a full relativistic formalism for four-component Dirac equation to capture spin-orbit coupling studies?
Okay, good question. Now, this development was done or led by Volker Bloom, so I think he should be the best person to answer that.
Yes. So first, the good news, so we can do four-component in the quasi-four-component method, which I'm actually quite proud of. And so Rundong Zhao led this, who's now at Beihang University, and there's a paper in 2021. And so it works for semi-local density functionals, single-point geometries, and for systems into the low hundreds of atoms in practice. And so, I mean, we've done a hybrid perovskite with no accuracy compromise up to 150 atoms or so. And I'm not sure that anyone else can do this, and this can be done for band structures. But for the full four-component method, we're actually quite interested in having a lot of things. So there's work going on treating open shell systems, which is needed. We need forces. We want to extend this to thousands of atoms. In fact, I will need this at least, and so I'm quite interested in doing this, and that's what we're working on. Forces are probably the most critical thing, and connection to hybrid functionals are also a critical thing that we still need to do. So for now, semi-local DFT like PBE and large systems with energy band structures and total energies work, and that's already quite useful.
Thank you, Volker. So another question from Robert. Can you recommend some papers for those wishing to learn more about green Kubo anharmonicity versus BT anharmonicity calculations?
I certainly can, because actually we had several very good PhD theses on this topic, but I think Christian will exactly discuss that, and I guess he may have some references on his slides. So I would actually, I mean, you can write to me later again after Christian's talk, and I can give you 3 or 4 papers, which I liked at least, but I think you will hear a lot on that of that in Christian's talk in the next presentation.
Exactly.
Yeah, and also just to say again, the tutorial tomorrow has some description of the green Kubo and BT theory in it, and there are also some references in this tutorial as well. Okay. Okay, another. Oh, and yeah, thank you also, Robert, for the comment that you're motivated to begin learning the software. So that's what we like to hear. Okay, so another question. So how does FHI-aims handle phonon-electron interactions in thermal transport modeling?
Okay, I have a talk on that, I mean, but I actually, honestly, I just really would like that you wait for Christian, because this is really part of Christian's. It's somewhat in this unfolding aspect, which I've briefly mentioned, but there are many little more aspects, and I think you will really learn exactly that in the next talk.